All right, so today we're going to be going over, it's a kind of a part two of a series we've started over terminal units and kind of airflow controls and automation. So my main presenter, Mr. Eric, is joining me front and center. But anyway, so we're going to be talking specifically about terminal units today and just the different types. Eric is actually a automation specialist and knows all the ins and outs of, more specifically Niagara. He's got a lot of background and experience. So I know a lot of our customers, y'all are familiar with Eric. Most of our employees are familiar with Eric. So.
Yeah, buddy. All right. Well, as Holden said, this is a kind of a continuation of a series we're running. Last month we talked about the air handlers in general and just the main air side of things. Today we're going to touch on terminal units, your metering devices for airflow in each space. I guess we'll just get down to brass tacks and keep it simple starting off. In a variable volume system, you have terminal units. The air handler provides air.
Black.
Sure, why not? Don't mind my drawings, they're rudimentary. Look, I said don't mind the drawings, okay? Okay, so this would be your air handler providing air to the ductwork. From the ductwork, we tap off and we have terminal devices. These devices meter the airflow to the space to control the space temperature, basically. There are two main types of terminal units. There are VAVs, which are just basically a box with a damper in it that modulates to control how much air goes through it. And then there would be a fan power box that has a fan in it and a damper to modulate airflow. Let's see, we will dive into these a little bit more. We'll start with VAVs. There are two main types of VAV boxes in a variable volume system. First is a normal, just single duct, has a damper in it, either a round or a square damper with an actuator on it that is going to modulate the amount of air going through the box. Two basic types, round and square. They both serve the same purpose. You could have pneumatic actuators, DDC actuators, doesn't matter. It's still considered a VAV box. There are two basic types of control for a VAV box. Well, actually, take that back. We'll touch on fan power boxes before we go down that road. So simplest way to think of it is VAV box is a variable air volume or variable volume terminal. It's just controlling the amount of air going through the box into the space. All of these boxes, if it is a true VAV, will have a crossflow sensor in the ductwork upstream of the damper that measures velocity pressure. And through math, which we'll touch on later, converts it to flow through either a, dang it, what's the pneumatic term? I'm drawing a blank. A velocity controller, or through an actual DDC controller, converts it to CFM readings, so forth. VAVs are real simple. They can have reheat, they cannot have reheat. Other than that, it's just a damper. The more complicated side of it is the fan power box. Oh, actually, you know what? Hang on. Back to the VAVs. Those were single duct VAVs. There are also dual duct VAVs, which are slightly more complicated because of dual duct. So a typical dual duct box will have two inlets coming from a hot deck, cold deck, and then these dampers will modulate together, and that mix the air inside of the box, and then it goes out to supply. Same basic thing, you have airflow pickups if it's maintaining flow, measuring velocity, pressure, converts it to CFMs, sends out how much CFM you want. They also, some of them, actually most of them, will just, they don't care about the temperature coming in as far as controlling temperature. They are still just doing flow. The logic can get real complicated when things don't work properly as far as supply air being fed in, either hot or cold. You have to know a lot more about what's going on in the space and with the air handlers when you're controlling with these.
Do we have any applications like that locally?
We do.
Okay.
Yeah, 310, 312.
You don't see too many of those.
No, it's pretty rare, and it's a pain in the butt.
Yeah.
Because when
So,
they,
with this system, is there two different air handlers, one for hot, one for cold?
some yes, some no. Typically, it's hot deck, cold deck air handlers. The air handler actually has two coils, a hot coil and a cold coil. So, and can also call them face bypass, all kinds of things. It's pretty uncommon, but you've seen those at the one building we're talking about, haven't you? You never been out there?
No, I don't know what you're talking
No.
Well, with a hot deck and cold deck, I mean, the coils will literally be kind of split in half.
Yeah.
So instead of being a full length coil or full height, the bottom half of the coil will usually be like the cold deck.
Yeah, you have like, you'll have an air handler and it's got, there'll be a split and then it kind
about.
of
Kind of a layer on
flies together.
the screen. Like, one of those two lights
Oh,
at the top of it.
Oh, yeah. I don't know if there's anything we can do about that.
It's just on RC.
gotcha.
Since you're drawing the ones
Yeah, well here, we'll move it down.
Draw it more your height.
I like drawing higher, it makes me feel taller. I have to lean down.
Don't lie, you don't have to lean down. Just look straight.
Think of it like that, and then this ductwork would come out and be split the whole way down into that box.
Not a super dark pen either.
No, I know, it's holding it, and
It's
there's,
not helping.
and there's pen choices here, making me use black. I'm more of a purple guy, but, and this is not to scale, it's rudimentary. Don't judge my third grade drawings.
It works.
Sometimes. 75% of the time it works every time.
And this would be used in place of like, so instead of the flow control being done at the air handler, which a lot of your older systems, most commonly, they would have these dampers at the air handler and they would just be offset. They'd be all done at the air handler. You wouldn't have a terminal unit downstream.
Yeah. So
This
this design was a way to try and fix Texas multi-zone setups and make it a little bit better control, but it's the same deal. It still sucks. but you can actually control flow in this instance.
Right.
Whereas a true Texas multi-zone, you're not
constant
controlling
volume.
flow, it's constant volume.
Right.
So these do have metering, these do control flow in the right circumstances. If the box is set up to control flow, it can control flow. Whereas a true Texas multi-zone does not control flow at all.
And hot and cold duct technology is basically pretty much obsolete at this point.
Yeah.
It's pretty rare to actually run into it.
Yeah, there's no real point for it now. There's a lot more efficient ways of doing things.
Yeah.
So, yep. So with the dual duct stuff, it's pretty rare, but we do get it. We have a few specific buildings that have it, and it is always problematic. Basically, you're increasing your failure points with any dual duct system. You've got 2 cross flows, you've got 2 controllers a lot of times, you've got minimum of 2 actuators if you don't have 2 controllers. If there are multiple controllers, they have to communicate to each other, they have to be talking back and forth. Typically, we don't like to do 2 controllers, we'll do 1 controller with 2 actuators, it's the best way to do it. Some of them, of the dual ducts, actually have a single actuator, and it's the damper is joined together. So, those are nice.
That goes back to the multi-zone concept.
Yeah. I don't know. Any questions on basic VAVs or dual duct setups? Nobody? Okay. Well, then we'll move on to the slightly more complicated side of things and touch on fan power boxes. There are 2 types of fan power terminals. Oh, that's something we can touch on first. FPB, FPT, FTP, VAV, a lot of these nomenclatures are synonymous with each other. Basically, if somebody says VAV, they can be talking about something with a fan in it, something without a fan in it. I've seen systems where every box in the system is labeled VAV, regardless of if it has a fan or not. I've also seen systems where you have no VAVs and systems where you have no fan power boxes. It really just depends. So don't just walk up to something and just because it says VAV, think it's only a VAV. It could be an old style VAV where they actually have a fan cut in further down. And if you don't know to look for that, you won't find it because it's 10 foot down the duct line. We get that sometimes where you'll have a piece of ductwork, VAV box, a little damper in the middle, comes out, and then somebody decided they wanted to be cool and put a fan in a little bit down the line. And it's now a fan power box. So that happens a lot. It's a way to retrofit in a fan power box, I guess. It's not really the greatest, in my opinion, but it works. We've got quite a few buildings that are set up that way. It's the same exact function as a complete factory-built fan power box. It's just 2 separate pieces. But as I said, just because something's labeled VAV doesn't necessarily mean it just has a damper.
And in this particular setup, your heat would be a
Yes.
part of the actual fan.
Yes. Yeah.
Okay.
Either draw through or push through, just depends on how they designed it. So, like we were saying, VAV, FP, actually, you know what, let's do this. Big. Huh?
You have to read it big.
Oh, I don't like drawing big. You maybe stick down to the bottom side of the paper. Yeah? What else have you heard called, Holden?
That covers anything I've heard.
So basically, if it's got an F in it, you're gonna think it's a fan. It's pretty given. So fan-powered box, fan-powered terminal, fan-powered VAV, I guess, would be what they were considering an FPB, VAV, or an FT for for a fan terminal. Oh, that's right. I've heard them called FTUs. I've also called. I keep making P's. FPU for fan powered unit. Yeah, FPTU. FP.
Why not?
No, I was working in a building today. They're all FPTUs.
Yeah.
It's just what the engineer decided to call them that day. What? Oh yeah, yeah, SPB.
SPB. SPB.
And then also, what else? Oh, it can be a TU as well, terminal unit.
Yeah.
Heard them labeled that. That one can be really confusing because we have one building, everything's TUs. Fan power boxes, VAVs, doesn't matter. They're all TUs because they're all terminal units. So, what else can I think of that I've seen crazy name-wise?
I think that pretty well covers the
We've
majority
got,
of those.
well, there's also constant air, CAV. So constant air volume, those are real popular in hospitals where they have to maintain airflow changes. Or also that could be like an exhaust VAV or an outside air VAV. It maintains just a single set point, doesn't care what the temperature of anything is. It's not even looking at a thermostat, it's just maintaining flow. Yeah, so there's all our fun random nomenclatures. Now, I will make some very childish drawings of fan power boxes. Spell that right?
It's close enough.
Yeah, but we're live. We're doing it live.
Yeah, I misspell stuff all the time.
Well?
It'll work.
Nope, that doesn't look right either. I like that better.
Okay.
Can you see both of these, Justin?
Yeah.
All right. So there are two types of fan power boxes, parallel and series. Oh, here we'll go. All right, two basic types, parallel, series. The easiest way to think of this is they either run in the damper and the fan either run in parallel or they run in series. In a series box, or sorry, in a parallel box, you have a split cabinet and a single outlet. You'll have a fan that draws from the return plenum and a damper that feeds your supply air. Inside of the cabinet, they mix together and they push out through the outlet. Either one can supply the pressure. In most cases, in heat mode, the fan runs. It does not run in cooling. In cooling, you're only getting air from your damper, and then it feeds through. And then in heat mode, your damper will usually back off to a minimum, or it may go fully closed depending on how it's engineered, and your fan will come on and push air out of the box. So the two items are parallel to each other. In a series box, They are in series. We once again have our one outlet, but we have a side pocket. Marker's going out. We have our supply duct with a damper in it, and then the fan pushes out. In this box, your fan runs all the time. Your damper supply air has to push through the fan. So let's see. Fan on in. Heat. On all.
The only other note I would add to that is on a parallel, you'll also have a divider here.
Yes,
with
usually there is a
backdraft.
backflow damper. Not always, but most. There's some that don't.
Yeah.
What does that do?
So when this pressurizes this cabinet, this is just a barometric damper, so it's just hanging. It just flops in the wind. When the fan kicks on, the pressure pushes it that way and it opens. Well, when the pressure comes from this way, it closes it and it seals. It's to keep it from flowing out the back. Series boxes do not have that. So if you walk up to a series box and you have air blowing out of the side pocket or return of the box, that means one of two things. Either this fan is off completely, not running, or it's turning too slow and the damper's providing too much air and the excess is blowing out of the side of the box into the return. That can be caused either by, like I said, the fan being completely off, the fan being too slow, someone has messed with the flow set points, or someone has messed with the fan speed. Go both ways. So, or it can also just mean it's out of calibration. So I guess there's technically three things that could cause it. Need better markers.
I'll try different.
No, I just want to complain about this.
Yeah, red in there. I'm not.
So, okay, the reason there are two types of boxes. Not super versed on this part of it because it gets more into electrical theory. But from my understanding, the idea behind a series box is that a fractional horsepower motor draws less current than your high horsepower motors in an air handler. So in theory, you can have a smaller air handler with a smaller motor when you have series boxes because you are shedding that load from the main air handler and putting it into the box. So you kind of get a pull-through effect for airflow as well as the supply air. Like I said, I'm not super versed on that. It's electrical theory. I'm not an electrician. I don't know how that works with the amp draws and whatnot, but that's at least what I've been told by an engineer, is that they can have a smaller horsepower fan for a given CFM with a series design system than a parallel design system, because you shed your load down to the fractional motors.
Well, in vast majority of the time, those fans are typically like an ECM design in a series setup. And so that you can have that ECM fan running, you know, just a couple of tenths of an amp
Yeah.
at proper load. And if you've only got 24 of those, I mean, you're talking a handful of amps, where if you can downsize a motor from needing a 60 horse to a 40 horse
Yeah.
by having series terminals, you know, it is a huge energy savings at that point.
It can be. So plus you can maintain lower static pressure with a series system than a parallel. Because like I said, you get the draw through effect. You don't have to have as high a pressure in your supply duct as you do with the parallel, because you're always pushing pure CFM through the box with a parallel, whereas a series, you've actually got a draw through effect as well.
Yep.
One thing to note, I've written it here, but anytime the building's occupied, this fan has got to be on. Anybody that tells you anything otherwise, don't believe them, don't trust them. They're wrong. Any engineer you ask, any actual mechanical engineer will tell you that fan needs to be on. Same thing with the guys that design the boxes. It's designed to run all the time. If someone shuts this fan off for energy savings, they may save energy, but it's at the cost of you're now not sending air downstream, it's blowing out the back of the box. You're wasting your cooling. You're just dumping whatever temperature air right back into the return. It's going into the unit's going to short cycle. You're not going to cool the space temp. You're only going to cool the return. You're going to have temperature problems. So you may save energy, but you are going to have other problems. Basically, you won't cool your space. Parallel box, your fan only runs in heat mode. Something to note with a lot of control systems, we have dead bands in the controllers where sometimes that fan may bump on and off, even though you're not actually actively heating. The fan is your first stage of heat. It will circulate return air to warm the space up before it brings on a physical heat strip. So just because you see a fan running does not necessarily mean there's a problem. Just because you're over your heating set point, that fan can still be running. Whereas a series box, your fan is always running no matter what. Series boxes are nice because they are constant volume, is another benefit of them. So you don't get that, the fan clicks on, the fan clicks off, customers complain about noise. Anytime you have an open ceiling environment, I definitely recommend series boxes because the noise, you can hear them, they're always running, you don't hear them click on and off like you do a parallel box. We get a lot of complaints when customers change systems from open ceiling to, a drop ceiling to an open concept with noise, with boxes cycling on and off. We've got a project right now that we're having some issues with noise because the tenant decided to move in and knock all the ceilings out, and sure enough, oh, we keep hearing these fans click on and off all day. Well, they're doing their job, keeping the space temperature, but you hear the fan come on. So it's one benefit of series over parallel, along with the energy savings side of it. I guess you could say there'd be less wear and tear on the fan because it's not starting and stopping on your contactor as much. Good benefit.
Well, that and almost the vast majority, this will be a PSC motor versus ECM. So where that'll ramp itself up, any kind of electric motor, I think it's like 80% of the wear and tear on that motor is the start and stop.
Yeah.
Specifically the start, because of the inrush current. Having it modulate up reduces that wear, but it is still wear having to get started.
Yeah. And we'll get into the different types of fan motors later. I'll cover that in a little while. Maybe we can cover it now, I guess. Yeah, it's fine. So, yeah, perfect gateway into that. There are three basic types. What was that nomenclature you used on that motor? A PSC?
A PSC, permanent split capacity.
PSC.
So if the series fan fails, is there anything we can do before switching out to get that airflow?
No, nope. I mean, you'll get some through the box, but it's gonna always take path of least resistance. And I have never seen personally a backdraft damper here. By theory of design, you would not want one. I've seen some people that have put like return boots that had them. Why they did it, I don't know. I'm assuming they just slapped them up there trying to resolve an issue and didn't understand the cause of the issue. And that was one job a long time ago in Houston, and they ended up ripping them all out when we did the tenant improvement on the job. So, yeah. But if this fan goes out, you're gonna push everything out that return. So that is kind of, I guess, a benefit in regards to, in this situation, with a parallel, if you lose your fan, you can still temper the space. You won't be able to do it during heat though, because typically you need the fan to do the heater, because you can't get enough, your airflow pickup is typically on the fan side for your safety, not on the damper side. Some of them are mixed up on they're actually on the cabinet, not the fan outlet itself, but it just depends on the manufacturer. So back to where Holden got us, there are PSC. Oh, that is bright. That is a horrible M. ECM. What other nomenclatures you got, Holden, for fan types?
Those are the two most common. Yeah, it's permanent split capacitor, and like I said, you'll have the most obvious sign for that is there'll be a literal capacitor. And your ECM is electronic commutated motor. Those have a control module that work very similar to how a VFD works. It's just kind of built into a really small package for a single phase device. So yeah, these will have an actual control module that run these motors, and he'll go into what the automation does to kind of help control the speed on that.
I'll stop you right there. Typically, we don't control speed.
Right.
As far as ramping this motor up and down through the BAS, we do not do. Typically, it's a kind of like a soft start in that system. Mm-hmm. They do have the ability to do it, and I'll touch on that in a second. But back to what Holden was saying is the best way to kind of think of it with a PSC versus ECM is these are on or off. These can modulate based on parameters in the design. ECMs are cool because if you have a dirty filter, they will ramp themselves up to compensate to maintain flow. That's one benefit, whereas a PSC will not. It's just going to run at whatever speed it may be. Some PSCs are a single winding, some have multiple windings, whereas you might have a low, medium, and high winding. Or they may have a, what'd you call it, a potentiometer, a rectifier, I guess it's a
Rheostat?
A rheostat, yeah. Rheostat or ostat?
Rheostat.
Don't mind my spelling, I did not graduate third grade. So PSCs are either single speed on off. Some of them, we have ways through the BAS to switch multi-speeds. It's very rare. Usually they're set during test and balance. Or it's got a rheostat, which is basically a potentiometer. You'll see it on the side of the box that the test and balance guy can come in with a screwdriver, turn that little knob. Some of them have LCDs. They can turn this little knob and it will speed the fan up or down by varying the amount of current that the rheostat allows to go through it. We typically don't touch those as automation. That's the test and balance guys. Like I said, same thing with low, medium, high. This will either be a dial or sometimes you have to actually physically move the leg. Just depends on the manufacturer of the box. ECM motors are, I guess for lack of better terms, like Holden said, mini VFDs, mini soft starters, however you want to look at them. Some of them, actually all of them, have inside a board very similar to a rheostat. They will actually send a signal to the ECM portion. It'll have a little dial that can be adjusted. They almost always have some form of LCD screen on it that will read out RPM or amp draw. And then a lot of times they will have a terminal block on them where I could land an input for a 0 to 10 signal or a 4 to 20 milliamp or pulse width modulation. And then I could ramp that fan based on a set of parameters that was provided by an engineer. But I think I've done one like that in 15 years.
Yeah.
Kevin, have you ever done a job with an ECM motor where you've actually ramped the fan through the automation?
No, I mean, you've done it through like a standalone thermostat that I think.
Yeah. Yeah. But never through automation? Yeah. I did one, it was for a lab, but I mean, that was 7 years ago in Houston. And it was one really weird circumstance where they were using that box for something they shouldn't have been using. But it is there, it is capable to do. But most of the time they just do it through this dial on the board. One thing about ECMs is 9 times out of 10, this board is going to be inside of the cabinet, whereas the rheostat is mounted externally on the cabinet. Some of these will be external. It just depends on the manufacturer, but these are always external.
I think I've seen Titus put those external.
Yeah. Okay.
I don't think I've seen anybody else do it, but I know.
It depends on if they're external, they don't have this feature typically. They're not, we can't do anything with them. Usually you'll open up your compartment and it's a green board inside with a bunch of wires coming to it with a Molex plug or something of that sort. If they're external, they're acting more like a rheostat than in that capacity.
Well, in the Titus ones I've seen, so it had, basically this was not much more than an interface.
Right.
And so it had the regular control module,
Inside.
and then that was just interfacing to it. It still had all the normal terminals and everything.
Yeah, inside the box, but external, okay. Yeah.
Right.
Yeah, so basically, I guess if you ever open up a box and you see a board with a whole bunch of terminal blocks on it
And tiny wires.
and tiny wires, it's more than likely gonna be an ECM motor. Whereas this rheostat will literally have two wires, and that's it. Like I said, most of these do not have an LCD screen. It's pretty rare. If they do, they're usually an amp draw, not RPM.
And one thing, so a rheostat, or a motor speed control, which has a rheostat in it, and it's literally all it is. It's just adjusting the amount of ohms going through it. And so basically it's, whenever you have a low, medium, and high on these, if you actually were to ohm the motor out on a PSC, you would see that the high has a lower resistance in its windings than the low does. And that's why it runs faster. So with a motor speed controller, we're able to increase the resistance on the common leg, which would be, basically like running the high leg through the rheostat. And by increasing that resistance, we're able to slow that motor down. A very common mistake that I see, technicians sometimes do is they end up turning that down too low. And what'll happen is, if the motor is already spinning, it'll continue to run at that slow speed. But the moment it turns off, that motor speed controller, because it has too high of a resistance going through it, is not enough to allow the motor to actually turn back on, and the motor just sit there until it overheats and burns up. So you have to be careful of that. And if you do ever adjust these or mess with them, you always want to cycle power on that motor so that it can you can verify that it'll actually turn back on and run with where you have it set. And to troubleshoot those, you just read ohms through it. That's all you got to do. If you have a set of ohms and you turn the dial and the ohms go up and down, then it's functioning. If you don't read any ohms through it at all, or it doesn't matter what you turn it, it doesn't adjust, then that motor speed controller's failed.
Yeah.
And those are the brass nuts basics on that.
Yep. So one thing to mention, personally, I don't ever recommend touching these. They're set through test and balance. If you touch them, then that balance is no longer valid and should technically be redone.
Until you have to replace it.
It's getting there. So if this ever has to be replaced, I recommend, it's where it gets complicated because you need to know what kind of flow the box is doing. You would need to know which grills are served by the box, and then you would need to calibrate that fan speed based on those air balance calculations. Also, if the motor changes, those need to be reset. So typically, if a motor changes by itself and you're not dealing with a burnt up rheostat, I wouldn't bother changing it, messing with it, but technically it should be reset. But to get it there without the proper tools is highly unlikely to get it back to where it should be. These are a little nicer because you get RPM if you know what it was at before, or sorry, because it is set to an RPM, once you put the ECM motor back in, it will go to the same RPM because of the way this board works with the chip inside of it. This is just simply changing resistance. So if the new motor has less resistance than the old motor, this needs to be recalibrated. Yeah, anything else?
A big thing that drives manufacturers to still want to use PSCs comes down to just pure cost. You're talking a $100 motor versus a $600 to $800 motor most of the time. So just based off of the cost alone, these are way more expensive. They're a lot more efficient, and if they're taken care of, you can get a long life out of them. But used to, at one point in time, you used to be able to buy just the modules or just the motor. And that's one of the changes manufacturers have done recently is, it's kind of like they've done on a lot of automotive stuff too. They used to, you could buy just the AC clutch assembly from the parts house for your car. Now they don't sell those by themselves. You have to buy the whole AC compressor. It was kind of the same theory. They were losing too much money just selling you the module or just selling you the motor, because the module is the expensive part, not the actual motor. So they stopped doing that. Now you have to buy the entire assembly as one whole piece.
Yep. That's fine. So let's see. That touches on fan speeds and types of fans. So I guess that will leapfrog us into heat on a terminal unit, or VAV box, or fan car box, or fan terminal unit, or whatever you want to call it. There are two basic types of heat control in a VAV box. We have one, all right. Two basic types of heat control: binary or analog. Binary is simple 1 or 0, on or off, true, false, start, stop, whatever nomenclature makes you comfortable. Second type is analog, modulating. It's a variable frequency, variable pulse rate, variable voltage, variable amperage, whatever it modulates, it varies. It has a scale to it. There are multiple types of binary and analog. We have single stage electric heat, we have on-off hot water valves, we have multi-stage on-off electric heat. Like you may have up to 3 stages in a box, you may have 1 or 2, it just depends on the design. Analog can be any number of the above. You could have a 0 to 10 signal driving a stager or a sequencer that is settable inside of that sequencer to fire multiple binary stages of heat. Just depends on how the box is set up. Focus on binary first. So binary is either an on-off, open-closed, hot water valve. Let's go. Stage. Heat or multi-stage. So real simple stuff. Your valve is usually 24 volts to open, string return closed, or it can be 24 volts open, 24 volts closed with a relay sending it normally open, normally closed. Single stage electric heat. You got a 24 volt relay that makes a 110 volt contactor, whatever, 240 volt, 277, 480. And then you can have multiple stages of electrical heat. Let's do. How to expand on that? You can't hold me, got anything? I mean, it's pretty simple.
We could talk about how we stage it, why. Like, so say the multi-stage.
Yeah. So, I mean, okay, as far as that, so in binary, if you have any fan power box except for a series box, I should say, any parallel fan power box, with staged heating, you will have 1 equals fan for the most part. The idea is that it will draw in return air and use that, which is at a higher temperature than space air, to try and bring the temperature up in the space without actively going to heat. Not every box is configured that way. Some of them bring them on simultaneously, but sometimes, more typical than not, your fan is your first stage of heat. As we deviate from set point, heating is what we call a reverse action control. So as the temperature goes down, so this would be temp, as it goes down, our control source, I guess, would be, signal. Well, it's because it's not really a signal, but we'll call it an algorithm. Our algorithm will increase. So if at this point you may have stage 1, at this point you may have stage 2, at this point actually, hang on, that's the other way around.
I was gonna say, that's direct
Sorry.
acting.
Scratch that, that's direct acting.
This way.
Whoopsie.
There you go.
There we go.
There you go.
All right. So at this point, we may have 1. At this point, we may have 2. At this point, we may have 3. So as your temperature goes down, you increase your output, or algorithms logic will bring on the additional stages. So a lot of times the fan is the first stage, or it could be literally the fan and the first stage of heat. As the temperature continues to drop, we would then bring on additional heating, which may be your first stage of electric heat, or it may be your second stage of electrical heat, depending on how it's programmed. And then as temperature continues to drop, we would then bring on the third, fourth, fifth, whatever it is you have. One thing to note about VAV boxes, so without going too far into it, a true VAV box maintains flow, whereas it appears they maintain temperature. You are really using space temperature versus set point deviation to adjust your flow set point. The heat side of it, however, purely focuses on temperature deviation. Doesn't really care about flow. It can be a flow algorithm in there as well, but as far as your reheats, it's going to be solely based on temperature. So temperature goes down, output increases. Yeah.
And the temperature we're referring to is typically going to be like a zone sensor somewhere on the wall.
Space tip.
Yeah.
Yeah. They rarely maintain discharge. There are some instances where we do, but it's few and far between. So, yeah. It's pretty stinking rare, actually. I'm trying to think of anywhere I've ever done it. We do have cutouts where we will cut them out at a certain discharge temperature, but we don't maintain a set discharge.
I've run into a few. Once it goes into a heat mode.
Right. Well, that's what I'm saying. It will shoot to not go over a certain point.
Yeah.
Like it'll have like a high temp cutout.
Right.
That can either be an internal safety where it will actually drop out the contactor, or it could be like in case of a modulating output, we actually start to drop that back down to maintain that certain temperature. So I guess we'll touch on.
So first stage typically is going to be fan. Second stage would be, say, your first stage of actual heat. Third stage would be your actual, would be a second set of heat strips coming on, and so forth as it continues.
All right. Now we will do. Analog or modulating. It can be a hot water valve. It can be an SCR here. It can be a what's there? What else could we have? Pretty much it. All right. So analog heat, modulating also can be referred to. We can have three basic types. Well, I guess it doesn't really matter. So analog is going to be a varying signal. There are multiple types of signals. There is, let's see, go with a loading. C,
What does
It's a silicone controlled rectifier.
We'll
Heater.
get to that. All right, so the basic types of, can you see that, Justin? Okay, your basic types of analog output are floating, 0 to 10 VDC, 2 to 10 VDC, 0 to 5 VDC, pulse width modulating, and 4 to 20 milliamp. Floating is pretty simple. Floating is pretty much pulse width modulation in a way to think of it. It's just depends on what type of device is taking the output, if you want to call it floating or pulse width modulation. But in our realm of things, if I have a floating output, what I'm doing is pulsing a 24 volt signal over 24 volt signal over a set amount of time. If you have an actuator that is a floating actuator, it will have listed on it a 90-degree time. So it's the amount of time that damper or actuator takes to travel from 0 to 90 degrees or 100%. And some of them are 60 seconds. You'll see that. 60, 90, 120 are pretty common time frames. So that's from 0 to 90 degrees. So closed to open is typically what they refer to when they talk about the time of travel in a floating actuator. So if you have a 60-second actuator and you want to open it to 50%, I would send 24 volts to that actuator for 30 seconds. And in theory, it will open to 50% or 45 degrees. And then if you want to close it, you send 24 volts to the closed side for 30 seconds and it will go back the other direction. They work great. Problem is they can get out of sync. These need to be synced up over a certain amount of time, because if the controller's going back and forth in position, sometimes your actuators aren't exactly 60 seconds, or they aren't exactly 90, or they aren't exactly 120. Or as time goes on and the bushings start to wear out, or the motor starts to degrade, or the gears start to get crap in them, stuff in them, you get build up on your actuators, whatever it may be. These time frames can either increase or decrease, which will put your actuator out of sync. So they need to be resynced. Whereas when I say resynced, we typically either sync open or sync closed. You'll send them voltage for a period of time greater than your travel time to ensure that it goes all the way to whatever position you were wanting it to. Usually the safest bet is to sync closed, because not every system will open 90 degrees. Some of them only open 45, so we have to change these travel times. If I have a system that's actually full open at 45 degree, then I would only run this damper for 30 seconds, or only run this one for 45, or only run this one for 60, based on that percentage of open at full. A lot of your VAV damper actuators are this way. Very few hot water. Mostly it's VAV damper actuators, just because they're cheap, small, just easier. I guess we do get some, but oh well, we're focused on VAV, so we won't go that route. The second most that we use is 0 to 10. Actually, any of these, well, we'll go, let's hit that first. No, it's modulating width. All right, so we'll touch on pulse width modulation. So pulse width modulation is, scratch this guy. So there's a couple different ways to do pulse width modulation. It can be volts AC, pardon me, volts DC. It really just depends on what the device you're controlling is looking for. But basically, if you look at a stretch of time, we'll go 0, and we'll keep things small. We'll do tenths of a minute, or tenths of a second, sorry. So that would also be 0, 100%. So in order to do pulse width modulation, like I said, it depends on what you are controlling. It's very manufacturer specific as to what kind of signal and what range of voltage you are giving. But the basic way to think about it is, if you look at in a 0 to a 100%, a lot of them are over a second. Well, a second can be broken up into tenths. So if you want 50%, you would send whatever that thing is for 5/10 of a second, and that'll bring you to 50%. Then it drops out for the next 5/10 of a second, then would pick back up on the next 5/10 of a second, and then drop out. So you get what we call a sine wave, basically, of a pulse. So 5/10 of a second, off for 5/10 of a second, on for 5/10 of a second, off for 5/10 of a second, on for 5/10 of a second, and that would get you 50%. That time frame varies based upon how much you want that output to command. So if you want 90%, then you would do 9/10 of a second. And these time frames also vary by component you're controlling. Some of them are tenths, some of them are in seconds, some of them are, it varies. They have what they call leading edge, trailing edge. There's a couple different ways to do it without getting real in the weeds. This is your basic thought process behind pulse width modulation. So,
And if you were in the field needing to test that, basically it's not something you could legitimately measure, but
It's
what
pretty
you
hard.
would see is your meter would just
Yeah,
be
you jump.
flashing in and out. You wouldn't get a true reading.
yeah, the equipment needed is an oscilloscope,
Yeah.
and they're about $4,000 for a cheap, well, for a decent cheap one, I should say.
Yeah.
There's cheap ones out there, and they work, but for a good oscilloscope, they're not cheap. So, I want to say a basic Fluke's probably $3,000 without all the accessories. But you can pick up some. They actually make some pretty cool little handheld ones. They look like old Palm Pilots. Pretty cool. Got one, but didn't last long. And they're not rated for high voltage.
Figured that out, did you?
Yeah. Yep. So that's basic pulse width. Like I was saying, it can be volts AC, it can be volts DC. Some of them are, like I wired up a heater the other day that was pulse width. It was actually an SCR heater that required a pulse width modulating DC input. So basically anything from 4 to 32 VDC would bring that SCR on and open the gate. And then what it was it wanted that voltage over tenths of a second, just like this scale. So for 50%, I would give it anything from 4 to 32 volts for 5/10 of a second, and it would run up to 50%.
And it didn't matter if it was 20 volts or 10 volts.
No, it could be 31 volts, or it could be 4.5 volts, or it could be 15 volts, or it could be 11. It just didn't care.
They're just looking at the modulated
It just
signal.
wanted that pulse. So, and then what's really funny is if you wanted to control that specific SCR I was dealing with, which was a Viconics, if you were, I don't know why you would do this, but if you did not have a controller that could do a pulse width modulation, you could, in theory, use a digital output and I guess a VDC transformer and put so this would be your solid state relay in your controller. And we could send a 10 volt signal in and out, and this would be our common over to our SCR, and you could just pulse that solid state relay with a 10 volt signal into that SCR to get it to work, which is actually what I had to do.
Yeah.
Because the controller we had did not have the ability to do pulse width except for through a solid state relay. So,
Which a solid state relay is just a triad.
yeah. And you do not want to do this with a mechanical relay because you will burn it up.
Yeah.
They are not meant to pulse that fast. Or that many times.
Yeah, well, just the mechanical travel time on
Yeah,
that
it doesn't
is
allow.
that
Yeah.
long.
But it would have been nice if that controller had a universal output that could have sourced its own voltage, and then it wouldn't have been a problem. But it did not. Honeywell does not have an output that is capable of that. So, oh well, no big deal. So that's pulse width modulation. So the next ones are pretty simple in the way they work. They are just a scale. The obvious difference being that 4 to 20 milliamps is varying current, whereas these are varying voltage. So this will be a set, they can be DC, they can be AC, but they're usually 24 volts of some type, whether it's VDC or VAC, depends on the equipment you're controlling. What that does is your controller fluctuates the amount of current that device is allowed to accept and changes how it works. But they work like we were showing earlier on a scale. So this would be 100, 0, 0, 100. As your output increases, your voltage would increase. Actually, sorry, that's 10. So we use a 0 to 10. Now, this is not always the case, but sometimes you can reverse them inside the controller, and you could have your high as 0 and your low is, sorry, actually we'll do that backwards. That way. So you could effectively change the direction of an actuator by flip-flopping that output from a high as 10 to a low as 10 and change the direction of an actuator by that. A lot of actuators have switches on them that do that as well, so you can get in trouble that way, but it does work.
It's handy for troubleshooting.
Yes, it is. Just to make sure it works, you can
Yeah.
flip that switch and it'll go the other way.
So that's your difference between reverse acting and direct acting.
Yeah. So a hot water valve will modulate between 0 and 100% of its travel to maintain temperature. An SCR heater, as was asked earlier, is a
Control.
yeah, is silicone spelled right?
Yep.
Rectifier?
Mhm.
Yeah. Oh, you know, why did I do it that way? Should have done it the cool way. Yes. Oh. All right, a silicone controlled rectifier. Basically, what these are is, Justin, you can see all the edge, right?
Yeah.
Okay. Look at all this spaced out here. Is a contact, in theory. As you send voltage to an SCR, the mechanical, chemical wizardry inside of it allows this contact to close, therefore allowing current through it. We call them gates, contacts, whatever you want to call it. It all means the same thing. I'm not particular, Holden may be. But like the one I did the other day, that was a 4 to 32 volts. Anytime you send in anything from 4 to 32 volts, the chemical makeup of that rectifier allows that contact to close and current to travel through it. Some of them have variable gates that allow different amounts of current through them. Some of them are simple open closed. Like the one I did the other night was open closed. It didn't matter what voltage you gave it, it did the same thing. Some of them, most of the ones on fan power box and VAV heaters though they do scale that gate. So it can open and close and change its resistance to allow more through it. I'm trying to think how to explain that.
It's basically just it's a solid state relay. At the end of the day, it functions very similarly to a triac, just a really big one versus a very small one. So it's rated for a 30 amps versus like a regular triac on an automation controller might be rated for half an amp.
At milliamps.
Right. So that's the simplest version of an SCR that really applies to anybody in the field without just being an electrical engineer.
Yeah. So but like I said, there are two types. Some of them are just open closed, and then some of them are actually vary. And then variable. So open closed or variable. The third type of heat would be a multi-stage heater with a sequencer. These can get real complicated real fast. They're not exactly the easiest to tune because it's usually your controls guy is driving this part, your output, your 0 to 10 or pulse width, whatever it may be, and then the mechanical guy is driving that part. And if we don't talk to each other, you can get each other screwed way up. So anytime I have a box that has that, I try and do everything I can to set it up myself and keep it a single person affair. The basic theory behind that is that you have a board with relays inside of it. And then each of those relays has a set of contacts. And then up here, I'll have an input board. And this is going to my controller. And we'll just focus on 0 to 10. I send this a 0 to 10 volt signal. And then inside of this board are usually adjustable trip points that I can turn a knob, and I can make this guy come on at 2, I can make this guy come on at 6, and I can make this guy come on at 9 volts. So where it gets to be a problem is if I'm trying to tune an algorithm inside of my controller to do something, and somebody comes and starts jacking with these numbers, my algorithm is shot. It doesn't know what to do, it's freaking out. I can't tune it because I don't know what it's doing. So they can be a pain in the butt. These are pretty rare on terminal units. You see them a lot of times on outside air handlers and things like that that have big staged heat, where you can't really use an SCR just because they can't take the amp drop. But what you'll get is you'll have a big contactor that's running your 480, and then this guy will run like a 120 volt loop through it, going to that contactor, pulling that contactor in. That way your main load is here. We do see them in fan power boxes though. I've come across a couple. They work. So it's nice if you have a bunch of heaters in a box and you have a small controller that may only have 1 or 2 outputs. These are handy. We also get, we didn't talk about, well, I guess it's an SCR in a way. We have, I can't remember what are those things called, the stupid little, I guess they're just a DC pilot relay, huh? Like we get the 10 volt relays.
Oh yeah, for the distance.
Yeah, we just call them a pilot relay. Well, no, like, So we did a job and we used the micro spiders, but we had 3 stages of heat. So on the 3rd stage of heat, because we didn't have outputs on the micro, we had to use an AO to drive a 0 to 10. I guess it was just a pilot relay. Yeah. No. But,
One of the main ways to know what you have, so I think it's pretty straightforward if you have a hot water valve versus, electric heat.
Yeah.
The biggest way to know without even opening a panel if you have SCR is they'll have a large heat sink attached to the back of that module. So the SCR, like I said, it's a solid state device. Usually it's a square about yay big, and there is a difference between a single phase and a 3-phase SCR module. So you have to be careful if you're ever replacing them, which one you have and which one you get, and they're very expensive. We're talking like $1,000 expensive. But they'll have a large heat sink just hanging out the outside of the control cabinet, and so if you walk up to a terminal unit and you see this weird looking strange aluminum device just hanging off the side of the control panel, you are almost guaranteed you've got some SCR type device, and that what that is that's a heater to reject heat. So if you ever say you'll have a building that gets re-insulated for any reason, they have to be careful not to coat that heat sink because it will cause that module to overheat and fail.
if they do dry fall,
Yeah.
ceilings paint and open architecture.
So it's very critical. Anytime you have any type of retrofit or anything in the building, you protect that heat sink so that that's gonna make or break that SCR's ability to survive.
Yeah, they're not fun when they blow up either.
No.
Okay, I guess, so that'll bring us into safeties because SCRs actually have a unique safety that staged heating usually does not. What time is it?
It is 7. We have about 30 minutes left.
Sweet. So I guess you're not gonna let me take a break.
Yeah, we kind of missed that.
Let's go.
So for those who are new to our class process, we usually try to take a break somewhere between 6 and 6:30-ish. We got to talking too much and missed that, so we apologize for that. But we'll keep rolling since we're already there. You also have fusible links.
Ah. All right, well, you don't have to talk about that one because I'll leave that up to you.
Okay.
Basic safeties for airflow. Basic safeties for heaters. One thing to note before we go into this is hot water usually does not have any kind of safety, at least as far as control. We're specifically mostly talking about electric reheat here. Hot water valves are usually just out there on their own. There's no safety inside of the control system. Your basic 4 types, I had 3, but Holden gave me a 4th, are airflow, high limit, primary contactor, and fusible links. So these 3 can actually play in with this one as a secondary, or this is how these 3 shut down the heat. So airflow is obvious airflow. You have a sensor in the box with a normally closed or open contact I guess in this case it would be normally open. Failure, it opens, yeah. With a set of tubes, a high and a low. And the high will go into the cabinet of the box and read pressure, with the low out to the surrounding area. As this pressure increases, that switch makes, closes a set of contacts, allows your control voltage to go through your safety to create the loop, and allows your heaters to run. There are two ways these can work. This can either kill your primary control voltage, or it can, well, I guess it's always going to kill your primary control voltage, but it can either kill the voltage straight through into your contactors, or it can kill a primary contactor's control voltage, therefore preventing voltage from reaching an SCR. This one throws people for a loop because they're like, oh, my contactor's not pulled in. Why not? And they just don't understand why. And then even when that contactor pulls in, then the heat doesn't come on, or this contactor pulls in as soon as the fan starts up, and they don't understand why. They think this should be off. The next one is obviously a high limit. As your heat strip increases in temperature, if it gets too high, a high limit will cut out. There are manual and automatic high limits. Manual reset obviously needs a manual reset. A automatic high limit can be used to control discharge air temperature. As that high limit gets to a certain point, it will trip and it will shut off the heater, allow it to cool down for a second, and then bring it back on. And it's a way to keep a box from putting out like 140-degree discharge air temperature when you only need 90.
And most of them are set anywhere between 180 to about 210.
Yeah.
It's pretty common.
Well, that's the manual resets. A lot of the autos are like at 110, 120. So, because they're, at least in fan power boxes.
Yeah.
So, not everywhere, but because like I said, they're being used as a limit for discharge air temperature. But the manuals are set up there so that you don't burn the system down. I'll let you touch on the fusible link, and then I'll dive into this.
Okay. Yeah, a fusible link so these could be used as, this is usually always a pilot driven device, so you have pilot or load bearing. The high limits could be either or. If it's a pilot duty, it's going to be used to kill the contactor. If it's being used as a load duty, the power that's actually going through to the heat strips passes through that high limit. And a lot of times you'll see both. You'll see one high limit will run the contactor coil, and the other high limit will actually control the power going through to the electric heat. Fusible link is always going to be a load bearing control, because what it is it has it'll be inside of the airstream, but you'll see a little ceramic disc sticking out, and it'll have two prongs on it, and it's literally it's a fuse. It's a heat driven fuse that comes back, and this is fairly old. You're not going to see this on any new stuff, but you see this a lot on a lot of your older systems. In the same way that a normal high limit would trip, a fusible link, once the temperature, usually this will be, say, around 210 degrees, once the coils that are within inches of this fusible link in the airstream heat that link up, it will melt internally, and it will stop power flow entirely. And yet, some of them you can replace without having to replace the whole ceramic. A lot of them you end up replacing this whole ceramic piece. So they come both ways. Another field term that a lot of my, I guess, more old school techs I've heard use is a teardrop safety, or a teardrop limit, because the general shape looks like a teardrop, but the fusible link is the proper term for it. So if you've got an older building, don't be surprised if you run into that. You just test continuity through it. Then they're pretty basic outside of that. They're just killing the physical power. So even if the contactor's pulled in, it's still, the heat's not going to run if that fails.
So then what Holden mentioned was pilot versus load. Go. So when he's referring to that, pilot would be your control source or voltage. Load would be your actual high voltage power. So when I talked about a primary contactor, these devices feed into the pilot side of a primary contactor, and the primary contactor can actually disrupt the load side of your system. So a lot of systems will have, let's go with a high limit. This can be our airflow switch. And then I'll have my relay. So then we got 24 volts feeds in. So your 24 volt loop of your control system going through your high limit, through your airflow switch, and then my relay. And when my relay closes,
Switch back to red.
huh? Nah, I'll be all right. That then comes into this primary contactor coil. And then if any of these break 24 volts, this primary contactor will open up, stop your 480, 277, whatever it may be, from getting to your heat strips and shut everything off. When I was saying that these throw people off is a lot of times on fan power boxes, all it takes to make this guy come on are these two things. You don't need your actual heat relay to be engaged. Your heat relay or SCR or something, whatever it may not be engaged. As soon as you have airflow, that primary contactor will engage. And people freak out and they're like, well, why is my heater on? It's not supposed to be on. They don't realize that there's an SCR or a pilot relay going to another contactor. Some of these can be mercury contactors in older systems. And then some of them will just be a definite purpose relay contactor.
I couldn't tell you the last time I ran into a mercury.
You want to see a whole bunch of them?
No.
I can name about 7 buildings right off the top of my head.
I couldn't tell you.
One of them is a project we're on right now, and it's a pain in the butt.
Yeah.
And then the one I did that SCR heater on the other day had mercury contactor. So, but yeah, so that primary contactor will, if you don't understand its function, can play havoc on people when it comes to troubleshooting. Because say you have an SCR, you can be sending all the current, all the signal you want to that SCR. If this primary contactor does not make, it's not going to do anything. Yeah.
That's pretty good.
Anything else on heaters?
No? So we did have quite a bit on the back half of the agenda to go over a lot more of the airflow control side and get into how we control the air. This was kind of a building into of, this is the principle behind the basic functions of terminal units. So we can expect next class, we would just kind of pick up there
Yep.
and go into more of the deeper side of the actual
Control theory.
branch duct system and the how that relates to the terminal units and the airflow control and what he does to go in and program that pit out to control it.